Let's just get this party started right away. Let me just say, if you have a question, please raise your hand, and I will do like those tennis sport kids and run the microphone and hold the microphone so you don't have to hold it. And without further ado, I'm really happy that our first speaker is Melody Chan. So while she gets mic'd up, let me just say Melody is a professor at Brown University. She's a good friend. We've done some math together. It's been really, really fun. And she's one of the most fantastic speakers I've ever heard, to the point that you know how contentious hirings in departments are. When she was on the job market, she came and gave a talk at CSU, and after that, all my colleagues were like, why don't we hire her? And I was like, yeah, fat chance. Here she is, Melody Chan.
Thank you so much, Renzo. That's the best introduction I've ever gotten. And thank you to the organizers for organizing this wonderful event. I'm so happy to be here. I was planning to give just a math talk. And as for community building, probably the best thing I can do is try to end on time, or perhaps even a little early, and donate some time to the coffee break. So that's my plan. And I was asked to give a sort of, keep in mind the broad audience and give a colloquium style talk. So I suppose I apologize to the experts, and I especially apologize to several people who were at a conference last week with me where I gave, I would say, the same talk. So I won't be offended at all if you decide to do some community building elsewhere. Okay, great. So I want to talk to you about moduli spaces in tropical geometry. And my goal here is to state two theorems on the topology of classical moduli spaces in algebraic geometry, whose proof used tropical geometry. And then I wish to reveal the transcendental nature of these proofs, and I will try to explain what I mean and make a case for that. Sorry. Going the wrong way, sorry about this. Okay, there we go. My collaborators in the two theorems that I will announce. First, it's joint work with Soren Galetius and Sam Payne. And the second one is actually joint with one of our conference organizers. So this was work with Madeline Brandt, Juliette Bruce, Margarita Mello, Gwen Moreland, and Corey Wolf. And this emerged from the Women in Algebraic Geometry collaborative research workshop at ICERM in 2021. And then a lot of the perspective of this talk is influenced by work of Frances Brown, so I want to acknowledge that up front. And what I'm talking about is stuff I'm excited about. It's been the subject of ongoing conversations with Frances Brown, Sam Gruszewski, Soren Galetius, and Sam Payne. So I apologize for talking more about what's sort of hopefully in the future rather than the two bullet points, which are recently completed work, but I'm just excited and I want to share it with you. So hopefully there will be some paper sometime that I can point you to. Okay, so let me get started. So I'm going to drop right into the statements of the main theorems without yet too much motivation. So the first theorem is about a space that might be known to many of you. It's the moduli space MG, a parameter space for isomorphism classes of Riemann surfaces of genus G. And our theorem is a theorem on the dimension of a certain cohomology group, H4G minus 6 of MG with rational coefficients. And our theorem is that these cohomology groups grow at least exponentially in G, so at least about 1.32 to the G. And just for a little bit of context, this was an unexpected result, and it disproved a conjecture of Kontsevich going back to almost 30 years, and a more recent sort of concordant conjecture of Church, Farb, and Putman, which actually, how does this? Yeah. Yeah. Okay, I'll just gesture. So the latter conjecture was a conjecture that actually predicted stabilization of these cohomology groups. And they had a result that proved that if stabilization occurred according to the maps they prescribed, that stabilization would actually be to 0. So our result disproves those conjectures. Let me tell you a second theorem. And this is with the authors shown. So this looks like a little bit more technical. So this is a theorem about a certain canonically defined subspace of, in this case, the compactly supported rational cohomology of another classical moduli space AG of abelian varieties of dimension G. This is, again, a classical space that's studied sort of very much in parallel to MG and EG related by the Torelli map. So this notation here refers to the weight zero compactly supported cohomology. And our results, as stated on this slide, are about spaces A5, A6, and A7. And they compute certain, they compute the cohomology in that range. And this is maybe hard to parse. There's a lot of data here. So I'm going to sort of repackage it in the form of a table. So here's the table. And here the p-axis is horizontal, the q-axis is vertical, and the p comma q entry shows weight zero compactly supported cohomology in degree p plus q of a sub p. And this maybe gives some indication of how our results fit in. So our results are again shown in red. Actually, everything from the column 5 and onwards to the right is a consequence of our work. And this shows everything that's known sort of currently in the literature about this portion of the cohomology of this classical moduli space AG. For context, that class in 3,3, if you can see it, was part of a computation of Haynes in 2002, which computed essentially entirely the cohomology of A3. And that's sort of all that was known up to the time of our work. And just again, for context, the work that we did actually already answers a question of Sam Gruszewski that was stated in a survey paper of his on the existence of cohomology in odd degree in AG, or in fact, any of its well-known compactifications. So let me just mention briefly that the nature of this conjecture is as follows. Often in algebraic geometry, we study cohomology classes that are in even degree being algebraic. It's a bit harder, at least from the algebraic perspective, to get our hands on cohomology classes in odd degree, which, for example, wouldn't arise as dual to classes of subvarieties. So this answered that question from Gruszewski.
Explain what the zero weight part means.
Yeah, actually, I was hoping not to, given the sort of the request to keep it broad. So, right. So, if you have a complex variety, then the work of Deligne shows that there's a canonical weight filtration. So, canonical filtration on the cohomology groups of that variety, and that depends on the actual variety structure. So, it's not just a sort of function of the, merely the topology. And so what we're doing is picking off the weight zero, so the lowest weight piece of that cohomology group. And roughly speaking, and this is actually the theme of the talk, that's the part that can be understood combinatorially through the combinatorics of an appropriate normal crossings compactification. But for expository reasons, I decided I'm trying not to go that way, and instead I'll describe that whole story through the lens of tropical geometry. Okay, thank you. Other questions? Oh, sorry, I was supposed to repeat that. So the question was about some more details on the weight zero compactly supported stuff. Okay, great. So the goal of this talk is to explain what are fundamentally transcendental techniques to find infinite families of cohomology classes in AG and MG. And this is ongoing joint work in conversations with Francis Brown. Sam Gruszewski, Soren Glaetus, and Sam Payne is very much inspired by the existing work of Francis Brown in a paper called Invariant Differential Forms on Complexes of Graphs. Okay. And so these fundamentally transcendental techniques in this work in progress, so I'm having a really hard time with this pointer, will give, there we go. In particular, this, I claim, infinite sequence of Qs, filling out some more of this mysterious table up the P equals Q diagonal. So now let me explain. Okay, so before I explain, again, apologies to experts. This was new to me until very recently, and this basic perspective has been really exciting to me. So let me recall for you or inform you if this is new, that's even better. The ways in which transcendental numbers can arise from the data from purely algebraic data of varieties defined over the rational numbers. And so I want to give you sort of the first example of this phenomenon, and that has to do with, this will be illustrated in the case of C star, the punctured complex plane. So consider C star. As we know, its topology is non-trivial, and in particular, its H1, its cohomology in degree 1, is dual to this loop that I've drawn around the puncture in the complex plane. So here, this, again, H1 is the one-dimensional Q vector space generated by the class of this loop that I've called gamma. Okay, so that we all know. Okay, so recall, this is, again, something that's quite simple, but is a useful perspective. C star is actually the complexification, the complex analytic space associated to a variety that's defined merely over the rational numbers. So let X be spec of, oh, this is close to the name of the conference. X is a spec of Q of X plus minus here. So this is the Laurent polynomial ring over the rationals. And then, of course, complexifying, we get back the punctured plane. But with a variety defined merely over the rationals, there's, I claim, another way to compute the Durham cohomology, sorry, the cohomology. This is the algebraic Durham cohomology. So let me just recall what this is. And here, the relatively simple formulation I'm using takes advantage of the fact that this is literally an affine scheme. So in general, one does something a bit more complicated. In the affine case, it's easy to describe. There's a chain complex here over Q, consisting of the relative differentials, the differentials in degree 0, in degree 1, and so on. This would continue over here. But in this case, X is one-dimensional, so I stop after degree 1. And let me just remind you what these are. So in degree 0, we just have the functions, Q adjoint T plus minus. I'm sorry, I failed to correct a typo. This X and this T are the same thing. And then in degree 1, recall that this is, you can compute this out. This is Q adjoint T plus minus times dt. So the sort of algebraic differential one forms on the complex punctured plane. And the arrows in general are the exterior derivatives. So recall this works just as in calculus. T to the n goes to n times T to the n minus 1 dt, which is true as in usual high school calculus. This is true for n not equal to 0. And then the algebraic Durham cohomology is the cohomology of this chain complex. So in degree 1, it's the kernel here mod the image. And so you can see that the image sort of, it's everything except for dt over t, exactly due to this condition n not equal to 0, just as in calculus. Okay, so this is Q, isomorphic to Q. So we've seen two different ways to compute the cohomology of this variety that was defined using equations over Q. And the sloppy thing to say at this point would be that these two vector spaces are isomorphic. That's true because they're both one-dimensional rational vector spaces, but they're not canonically isomorphic as such. What they are, so they become canonically isomorphic after tensoring with C. And this is, let's call it the Grothendieck-Durham isomorphism. And this is in the case of smooth varieties X over Q. And recall, this isomorphism comes from integration and is familiar from undergraduate complex analysis. So in our running example, this isomorphism of the two copies of Q after tensoring up with C is exactly given by integration. So it says that this differential one form acts as a machine for turning, the loop around the puncture gamma into a number, and that machinery is integration. And as you recall, integrating dt over t around that loop gives you a transcendental number, 2 pi I, as recalled from undergraduate complex analysis. And I just never appreciated this until, very recently, that this 2 pi I is a transcendental number that arises merely from as a comparison, as a coefficient of a comparison theorem, comparing two different ways to compute cohomology of a variety over Q. Such a number is called a period, as discussed in a survey work of Kontsevich and Zagier from 2001. And again, perhaps I'm telling things to experts that you know better than I do, but this sort of is new and exciting to me. So I can't resist adding this slide. So periods are numbers arising from integrating an algebraic differential form on a smooth variety x over q along some singular chain. And to say this correctly, I should say possibly relative to a normal crossings divisor, again defined over q. So again, as in the previous slide, periods are the numbers that arise as coefficients of a comparison theorem on cohomology for varieties over q. And they're mysterious, so you can read more about these. This is a mysterious ring of numbers. It includes all elements of q bar. It's a subring of C because of the definition. And this is a countable ring because everything in sight is finite type over q. But it's hard to prove that any particular transcendental number is not a period. So for example, E is believed not to be a period, but this is not known. Great. Yes?
Has it been shown for several numbers that are known? Has it been shown for some numbers already that they are not a period? So as you say, it's hard.
Yes, a few. That's correct. Yes. But for most of them, it's not been shown. So the question was like, are there complex numbers that are known not to be periods? And I think that's correct. Yes. Great. Yeah.
So if I understand correctly, does this mean that all periods are computable?
If I understand that correctly, then yes.
So that would give lots of examples of complex numbers that are not periods because they're not computable numbers, right?
Oh, I guess, yeah, I suppose you're right. Yes, okay. Okay, great, thank you. Okay, so, as we saw in the sort of cartoon example in the last few slides, one way to detect cohomology is by integration of appropriate differential forms. And that's what I want to do. And now let me introduce the main spaces in question, which are the classical moduli spaces MG and secondarily AG. So let's recall the definition of MG. So MG is a parameter space for Riemann surfaces, by which I mean a complex manifold, compact and connected of dimension 1. So they look like this. And recall that there is a discrete invariant of Riemann surfaces. They're genus. So every Riemann surface, forgetting the complex structure just for a moment, is just a surface. It's oriented because you had a complex structure on it. And your oriented surface is homomorphic to a connect sum of G tori. And G is that number. G is called the genus, number of handles. And that's the only discrete invariant of Riemann surfaces. And let me recall that there are many different ways, so many different equivalent descriptions of the object in question, many different sort of categories that are equivalent. I described something sort of analytic, isomorphism classes of Riemann surfaces of genus G. This is the same thing, and of course this is sort of deep, that this is an equivalent category to the category of isomorphism classes, the category of smooth projective algebraic curves of genus G. Or alternatively, hyperbolic surfaces of genus G up to isometry. And here let me assume G is at least 2. Okay. Yeah.
Is something that is
Is there something that goes wrong for G equals 1? I'm not seeing
No, I just have to be a little bit more careful. Like, for example, with the hyperbolic structure it depends on G being at least 2.
the first two things, the first two things would be finite.
Yeah, so in a moment, I would like to, well, okay, let me just do it. MG, for G at least 2, will denote for me the moduli space, so a parameter space for isomorphism classes of Riemann surfaces of genus G. And for these nice statements that follow to hold, I need G at least 2. So certainly other things can be said for example, M11 or M0n for n at least 3, etc. Okay, there's a lot to say about MG. Let me just hit the very, very high points. So you can regard MG in probably in your favorite category. It's fine to think of it as a variety or an orbifold, or better yet, a Deligne-Mumford stack, in fact, defined over spec Z. It's irreducible as a complex variety of complex dimension 3G minus 3. And it was already known in broad strokes to Riemann, who apparently coined the term moduli. But of course, there's centuries of deep work on MG, including a rigorous construction that came much later after the time of Riemann. Many mysteries about MG remain. So here's a favorite of mine, a result of Harrer and Zagier from the 80s that shows that the orbifold Euler characteristic, so the Euler characteristic taking automorphisms into account, of MG is this exact quantity. So this, this number here, can't get it, that B sub 2G is the 2G Bernoulli number. And their paper furthermore shows, so that calculation above is an exact calculation, but it's actually true asymptotically for the ordinary Euler characteristic. And computing out the asymptotics of the exact formula, you see that, first of all, chi of MG alternates in sign with the parity of G. And second of all, that its magnitude is super exponential. It grows like G to the 2G. And at the time of the writing of that paper, so they already remarked that, in fact, no non-zero cohomology groups in odd degree of MG were explicitly known at that time, which is remarkable. Let me just sort of spell it out for you, because when G is even and large, the Euler characteristic is very, very negative. So we know that there's tons of odd cohomology, but again, it's very hard to detect. And in fact, the first non-zero cohomology group in odd degree of MG is due to Ursula Tomasi in a 2005 paper, where she finds a cohomology group in odd degree of M4. So these are, well studied, but yet highly mysterious spaces. Yes.
This is too naive, but maybe does MG not satisfy a kind of Poincare duality where odd would cancel out with odd over here, or does this not work that way for MG?
So it's not compact.
It's not compact.
Yeah.
This MG is not the compactified MG.
No. So here I'm parameterized. Let's see. It's a moduli space for smooth Riemann surfaces. Yes, of genus G.
The power of our queerness is over the technology here. So can you amp it down a little bit?
How does this thing work? Oh, there we go. I got it. Okay. Got it.
Morning rain.
I thought I will survive without start playing at this point.
Should we just turn it off? Okay. Okay, perfect. So that's just to orient us towards, this one of the big mysteries about MG. This is related to the problem. I don't have a slide on this, but it's related to the problem of finding unstable cohomology classes in MG. So unstable in the sense of, well, okay. Let me not get too far into that. But any odd degree classes would be unstable. And I really like the tagline that here is due to Benson Farb, that this is sort of the dark matter problem for MG. That we know that there's tons of unstable cohomology, but we don't know where to find it. We know it's there because of Euler characteristic considerations. Okay, and our results did shed some light on this question, producing the next known odd degree cohomology classes in MG after the work of Tomasi. Okay. Now it's time to turn to tropical geometry, which is the business I'm in. So let me give you a tagline in case it's new to you. Many possible taglines exist, but here's one. For me, tropical geometry is a degeneration technique in algebraic geometry. The idea of degeneration techniques is, of course, not new. It's not something that is, something that had its heyday in the 1980s, and of course, with many interesting developments since then, due to the work of Harris, Eisenbud, Mumford, and others. But I view tropical geometry as a sort of extreme degeneration technique in the sense that it associates a limiting object to a family of algebraic varieties that's entirely combinatorial, has no algebraic data remaining. Okay, so let me define for you now a tropical curve, and I'll try to do it through this picture. And in the offing is the definition of MG bar, which was alluded to in the previous question, but I'm actually trying not to do it that way. I'll try to do it sort of purely geometrically. And essentially, I'm doing it via the complex of curves due to Harvey. So let me explain what I mean. Here on the left, I have a poset here. This is a Hasse diagram of a poset. So the elements of the poset are collections of simple closed curves, non-trivial, pairwise, non-isotopic, non-intersecting, sitting on a genus 2 surface. And of course, there are infinitely many of these, but sort of combinatorially, there are only finitely many. And I've shown each of the 7 combinatorial types here. And associated to such collections, we have the associated combinatorics here on the right of the dual graph. So let me explain the dual graphs, perhaps just by example. Let's do this one here. So the dual graph is obtained by collapsing the closed curves that you drew on your surface to a point. And then what you get is a sort of singular complex analytic space. It has 2 irreducible components corresponding to the 2 vertices on the right. And each vertex is marked by a number 1, which denotes the genus of each of the components. And there's an edge crossing between the 2 vertices corresponding to the closed curve that we contracted. Is that fine? So here you see the 7. Hopefully you can piece together the definition from the verbal description and the example. So you see the 7 dual graphs associated to these collections of simple closed curves. Is that okay? Okay, great. So then for me, a tropical curve of genus G, definition, it's one of the gadgets that would arise on the right-hand side. So it's a vertex-weighted graph arising as a dual graph from a surface of genus G, plus an arbitrary assignment of lengths to edges. So I mean just a formal assignment of positive real numbers to each edge. So that is, for me, a tropical curve. And I claim that that's a useful sort of limiting object associated to a possibly degenerating family of Riemann surfaces. Okay, let me put in, I think I put in an orientation slide. Oh, no, sorry. First, let me tell you what the moduli space of tropical curves is. And again, I'm going to try to do it sort of by picture. So this is a picture of M2 trop. So this tropical moduli space, M2 trop, is again, it's a combinatorial moduli space. It parametrizes isomorphism classes of genus G tropical curves. And so drawn here is the so-called link of the tropical moduli space. So let me back up a little bit. So, in this example, we have sort of 7 combinatorial pictures in the top right. And one wishes to, for each picture, one at a time, one wishes to parameterize all possible metrizations of that given graph. So all possible assignments of positive real numbers to the edges. And that can be done, and you get some kind of cone-like space. I mean, it's a cone, possibly with some automorphisms. And that's a sort of subtle point that is not too important for the purpose of this talk. But maybe it explains the picture a little bit. So for example, consider the theta graph in the top left. There are a priori, three different, you can put three different positive real numbers on the edges of the theta graph, but in fact, each such assignment is the same up to isomorphism as 5 other assignments. So that's why I drew the resulting moduli space as one of the 6 barycentric cells. I hope that's clear, but it's not too important. So again, roughly speaking, the moduli space of tropical curves is glued together from a bunch of cones. That gluing comes exactly according to the Poset combinatorics as shown. And because these spaces are always sort of generalized or roughly speaking cone complexes, I will draw them by their links or cross sections. So what I've drawn is the so-called link here. It's identified with the space of tropical curves that are sort of normalized total edge length 1. So now you have an actual picture of the link of M2 trop here. I hope this suffices as sort of intuitive stand-in for a formal definition. Is it okay? Great. This is a slide in case you've seen other talks on tropical geometry and are baffled by the difference. So if you haven't, just ignore this just for a sec. So sometimes people give talks on tropical geometry and the objects in question look like this. And that's very different from what I'm doing. I'm studying metric graphs. Other people might be studying sort of polyhedral complexes embedded in some Rn with some balancing condition. So in case you've seen those talks, I just want to orient you as follows. This is my orientation slide. So I'm studying in this talk the bottom left in this 2x2 square and its relation with the top left, which is the sort of abstract Riemann surface picture. If you had asked an algebraic geometry like 250 years ago what an algebraic curve was, it might have been something more like the top right. It's some 0 set to a homogeneous polynomial of degree d, with 3 variables in P2. And the tropical picture on the bottom right is more of an analog to that. So there's sort of, just as in in algebraic geometry, there's sort of either the abstract curve picture or the idea of a curve already embedded in a projective space. And just as in algebraic geometry, studying the sort of difference between the left side and the right side is of interest. So in the algebraic setting, going from the left to the right above is, roughly speaking, the theory of, very roughly speaking, it's Brill-Noether theory, the study of ways to put curves into projective space. And just to orient you, there is an interesting tropical Brill-Noether theory, which is the work of many authors, including Matt Baker. And very roughly speaking, that would sort of connect to the picture that I'm talking about with the perspective that you may have seen in other talks. Okay. All right, getting back to the main thread. So what have we done so far? We introduced MG and we introduced MG trop. And now I want to tell you an actual map between the two spaces, a proper continuous map of topological spaces. This is a stand-in for going on about wave filtrations. But this works. Okay, so let me define a map lambda, and it goes like this. So before we start, let's pick a very small number epsilon greater than 0. And having done so, the map goes like this. So suppose you have a Riemann surface reinterpreted as a hyperbolic surface. So there are potentially some geodesics that are short, have length less than or equal to epsilon. And my map will go by collapsing those curves and then taking the dual graph and metrizing appropriately. So it's not too important what I wrote there. The point is that as the curves get shorter and shorter and shorter, the corresponding edge lengths get longer and longer and longer. And the assertion that is in the offing that I didn't make explicitly is that there exists some sufficiently small epsilon so that any two short geodesics of length less than or equal to epsilon are disjoint. That is a true statement about MG. So having said that, we actually have a map of moduli spaces directly from algebraic to tropical. And it's a proper map. It induces a map on compactly supported cohomology. And then by taking advantage of Poincare duality on the one hand for MG, passing between compact supports and usual cohomology, and taking advantage of the sort of relationship between the cohomology of MG trop and its link, I claim that we have an induced map like this. And it's not too important, it's not too important in the context of this talk for me to convince you of the details of all the degrees and stuff like that. But let me assert to you that this map turns out to be a surjection, as you can see in my paper with Galatius and Payne. And again, abstracting out all the detail, the point now is this. We have a surjection from some algebraic cohomology group to some combinatorial cohomology group. So if you can find a bunch of stuff on the right-hand side, then you also know that you have a bunch of stuff on the left-hand side. And that's the game we play. Okay, any questions? All right. So the top part of the slide is what I just said. Okay. So the next section of the talk is very much inspired by, and it follows, Francis Brown's recent paper on differential forms on complexes of graphs. And so in some sense, I have no business talking about it, but I think it's very exciting, and hopefully there will be more to say soon. How are we going to find homology classes in the link of MG trop? In the story that I'm presenting here, we shall find them in the spirit of the slides I presented on the punctured plane. We'll find them by integrating actual differential forms on the tropical side. And in fact, our differential forms are going to be pulled back under a tropical Torelli map from MG trop, which is a space I have defined, to another tropical moduli space as of yet not defined called AG trop, the moduli space of abelian varieties of dimension G like tropical abelian varieties. So my next job is going to be to explain that map. And it's a very sort of pleasant elementary combinatorial description. All right, so let's back up and do some combinatorics. So suppose I have a genus G graph G, meaning a graph that's homotopy equivalent to a wedge sum of G circles, so dimension G cycle space. And I have some metric on it, L. And I'll orient the edges for reference so that then I can speak of H1 of the graph as just formal sums of edges having zero boundary. So just a one complex in the topological sense. Let me tell you what the Jacobian is of a tropical curve. So there's a natural, given the data I just said, there's a natural positive definite form Q on the cycle space. And it's roughly a dot product. So given a formal sum of edges and another formal sum of edges, it roughly goes to the dot product, as you would expect. But it's a sort of weighted dot product weighted by the lengths of the edges. And these are, remember, positive real numbers. So this is positive definite simply because it's the restriction of an evidently positive definite form on the whole edge space, just because the edge lengths are positive. And to record this positive definite form on H1, you can do it as follows. So H1 has a natural lattice structure. H1 over R has a natural lattice structure, H1GZ. If you choose an integral basis for the integral cycle space of a graph, you get a positive definite matrix representing your form Q. And here's an example that I drew. Sorry about the bad picture. This is supposed to be a picture of a theta graph, 2 vertices, 3 edges. The edges are called E1, E2, E3, and they have lengths A, B, and C. And then I chose this basis for the integral, this Z basis for the cycle space. And I get the 2 by 2 matrix on the right, the bottom right. So for example, this A plus B in the top right is essentially it's the dot product of this and this E1 minus E2 against itself, but with the edge lengths taken into account. Is that fine? And similarly, the minus B off the diagonal is essentially the weighted dot product of these two entries. Again. Okay. So we chose a basis, and had we chosen a different basis, we would have gotten a different matrix, which is related to the original matrix by an action of the general linear group, GLGZ, which is the integer change of basis group. So specifically, it's related by sort of X goes to A transpose XA, as you can calculate out in this example. So the matrix itself is not canonically associated to the metric graph, but the matrix, the class of the matrix under this action of GLGZ is canonically associated to the graph. And that's exactly the Jacobian of a tropical curve. So roughly speaking, I've suppressed one tiny detail, but at the moment we have a well-defined point in not the positive definite cone PDG, but the quotient of that cone by the action of the general linear group, GLGZ. And this quotient is, approximately speaking, the moduli space AG trop. And I just made one sort of expository, I elided one thing for expository reasons, which is you saw that the dual graphs could actually have genus at less than G when there are vertex weights on the vertices. So actually the moduli space AG trop includes some positive semi-definite matrices that are obtained by padding by zero appropriate positive definite matrices. But roughly speaking, AG trop is just the quotient of the positive definite cone by this action of GLGZ. And the map that we just described associating a Jacobian to a given curve is the tropical Torelli map, again, approximately. And this is a picture that was in my thesis. So I've been studying the same thing for the last 10 years. So these are all the dual graphs. So these are the cells of M3 trop on the left. It's the analog of the 7-element poset in genus 2, but here in genus 3. And then on the right is a poset of cells of A3 trop. And the color coding is according to the fibers of the tropical Torelli map. So I didn't explain A3 trop. I mean, I didn't even draw AG trop. You should roughly picture it as a positive definite cone, if that's true up to this discrete action. But it turns out that a part of AG trop is sort of closely related to cographic matroids. And the graphs go to, the cells of M3 trop are sent to the cells of A3 trop, actually just according to the matroidal data of the associated graph. So for those who care about matroids, you can hear in the description that I previously gave of the Jacobian that the whole construction only depended on the matroid associated to the graph. It only depended on the edge set and on which subsets of edges form cycles. Therefore, it's a matroidal construction. So that perhaps explains this colored picture for those who are interested. Okay, so let's get back to business. So here are the forms we're going to pull back. There are particular smooth differential forms in degrees 5, 9, 13, 17, and so on. So in degrees 4k plus 1. And these are forms on the positive definite cone, and they're defined in this way. So here, so I wrote omega k is trace of the quantity x inverse dx to the k. This is a differential k form on the positive definite cone. And here x is just a symmetric matrix. So it's sort of, this is relative to, the coordinates on the positive definite cone. And so here I just tried to write it out in one example just so we can match up the data types. So, this form defined on, a symmetric matrix with coordinates x1, x2, x3, x4, x5, and x6. You get it like this. You take the inverse of that matrix, which is, some rational function, some matrix of rational functions in the xi. You multiply by this d of that matrix, then you take the fifth power, sort of fifth exterior power. So now you have a matrix of 5 forms, and then you take the trace. So you have some 5 form defined on the interior of the positive definite cone. And these are very special forms. They're among other things, they're invariant under the action of GLGZ, that action that I just described, taking a matrix X to A transpose XA. And the reason that they're significant for us is that they freely generate, as an exterior algebra, the stable cohomology of this arithmetic group, GLGZ, I believe by the work of Borel. So these forms can be integrated on tropical moduli spaces. And my reference, again, for this section of the talk, is work of Francis Brown. So let me describe what I mean. So for a graph G, you can take the form that we just described on the positive definite cone. It's GLG invariant, so it actually descends to the tropical moduli space, and pull it back along the Torelli map that, again, we described combinatorially. And sorry, I should have drawn a picture, and I failed to. So this form that you get, I regard it as a differential K-form on the projective space with coordinates equal to the edges of the graph. So remarkably, how to describe this? This form, in general, might have some poles, but it's actually well defined on the real unit simplex, which sits inside this projective space. So by real unit simplex, I mean, again, it's like the points in projective space that actually are represented by, tuples of real numbers, non-negative, summing to 1. This is some sort of relative chain inside this complex projective space. And then integrating the pulled back form over this simplex, again, by definition, it's actually another example of a period. And I should be a little careful. There are poles sort of potentially on the boundary of the simplex, but Brown proves that there's an appropriate blow-up to resolve those poles. So I think the point of this slide is that we can integrate directly on the tropical moduli space MG drop by pulling back Borel's differential forms along tropical Torelli map. And these integrals can again be transcendental. So proof of concept, this can be interesting. This is my favorite class of graphs at the moment. For each G, at least 3. Let me let WG denote the G wheel graph. It's the graph obtained by taking a cycle of length G and adding an apex vertex, and they're drawn here. And now here's a remarkable theorem, not due to myself. This is in progress work of Francis Brown and Oliver Schnetz that they've announced 2022, which says that for G odd, if you do the thing we just described, and you integrate the pullback of omega 2G minus 1 on the simplex, the real simplex associated to the wheel graph WG, you get this exact number. So for my purposes, what's important is that it's non-zero, but it's actually this remarkable transcendental number. It involves the actual zeta function. And it's a zeta function, zeta of G times some integer. And then I claim that, like, again, in the spirit of the slides on C star. Oh yeah, question.
Were those zeta values all already known to be transcendental?
Yes, I think the point here is that these are not the zeta values that the physicists would have expected, I believe, in the context of Feynman integration. But here we actually do get zeta of G associated to the wheel graph on G vertices. I don't know the internal workings of this calculation, I'm sorry to say. So for my purpose, this remarkable calculation and the fact that in particular you get a non-zero number explains some of the cohomology that we found with Galatius and Payne. So this is a restatement of that theorem. And this non-vanishing recovers in the way I've set up this talk, it recovers part of the result joint with Galetus and Payne, which is the non-vanishing of these cohomology groups in exactly the genera that the theorem refers to. And the whole machinery that we've described sort of is relevant here, the machinery that to find a non-zero cohomology class on the algebraic side, we find a non-zero homology class on the tropical side, but that was found by integrating an actual differential form on the appropriate tropical moduli space. That integral is itself a period, as described in the slide before. And then, I will call this work in progress with the authors I mentioned. You can do the same thing on the side of AG, which is space I didn't focus on too much. But essentially, by not pulling back by tropical Torelli, but just working directly on the positive definite cone, which is roughly speaking the tropical moduli space AG trop, you actually get, again, some new, this is actually new work here. It's a new infinite family of non-vanishing cohomology groups of AG for G3, 5, 7, and so on. Okay, so that's the story I wanted to tell. And then let me just mention a little more what was going on in that 6-author paper I mentioned with Madeline, Juliet, Gwen, Corey, and Margarita. The story I just told on the previous slide here is a story, when you look at AG, it's a story about relating the cohomology of AG somehow with the cohomology of an arithmetic group, GLGZ. Recall that the cohomology of AG with rational coefficients actually is the cohomology group of a different arithmetic group. So one way to construct AG, it's sort of analogous to the Teichmuller sort of quotient construction of MG. One construction of AG is as a quotient of the Siegel upper half space, which is some contractible complex space, by the action of the symplectic group, SP2GZ. So through this story, if you're studying the cohomology of AG, you might as well be studying the cohomology of the symplectic group. But of course, the advantage, if you will, of looking at AG is that you have the complex variety structure, which, as we discussed, has some extra structure. So our program, the program that we started in this paper, it's a sort of, I think, new in the literature relationship between cohomology of two different arithmetic groups, SP2GZ and GLGZ. And there's one more player in this story that I want to just take one more slide to discuss, because it's just a cool story, still partly conjectural. And that's the cohomology of a certain compactification, the Satake compactification of AG, also known as the Bailey-Burrell compactification. That's point 3 on this slide. And all these connections come through the study of the tropical moduli space AG trop, and our work has dependencies on many important parts of the literature, including computational work by the first 4 authors there, EVGS, and then earlier work by Charney Lee on cohomology of AG Satake, and more recent work of Chen and Lohenga. So okay, AG Satake it's a compactification of AG. I want to black box it for the purpose of this talk. It's some complex variety that has a stratification into AG, AG minus 1, and so on, these locally closed strata. And so there's a spectral sequence associated to this stratification. And now let me reveal that the table of data that I presented in slide 3 or so is actually the E1 page of that spectral sequence, which would converge to the weight 0 cohomology. Sorry, this should say, no, this is correct. The weight 0 cohomology of the Satake compactification. This was a connection pointed out to us by Ursula Tomasi, for which we're very grateful. So what's conjectural about this picture? So on the left is E1, that's sort of what we computed so far. And on the right, it's E infinity. That the placement of those classes is conjectural, but due to the work of Charney Lee and Chen Lohenga, it's known what the cohomology is in weight 0. And so you can see the sort of like diagonal classes that we started finding in the 6-author work, and we're continuing to find thanks to these integration techniques. Conjecturally sort of approach, converge on E infinity to the weight zero cohomology, the Satake compactification, sort of along that p equals q diagonal. So that's conjecturally what we're picking up through these among other things, these wheel integrals. All right. Let me go back to the main thread of the talk. So, when I started this like line of work many years ago, I was really interested as a combinatorialist at heart that one could obtain calculations on things like cohomology of MG by appealing to purely combinatorial calculations. I didn't emphasize the pure combinatorics in the context of this talk, but you can imagine that if you have some sort of cellular combinatorial moduli space where the cells are indexed by graphs, there should be some cellular homology theory that produces some finite combinatorial chain complex whose generators are graphs, whose differential is some graph theoretic thing. It turns out to be edge contraction. And that's true. And one thing that we did in the joint work with Galetis and Payne was to use that perspective to connect to existing complexes of graphs introduced by Kontsevich in papers in 92 and 93. So Kontsevich's graph complexes, again, there are some finite rational chain complexes generated by graphs. And so I was very excited by this and tried to get my computer to do various things, doing computations on graphs to produce cohomology in MG. But as a combinatorialist, I've come around to the necessity of looking more broadly at transcendental techniques to understand even graph complexes. So here is a screenshot of a paper that I'm not connected to at all. This is work of 3 physicists, Buring, Kiselev, and Rutten from 2017. And the paper is called The Heptagon Wheel Cocycle in the Kontsevich Graph Complex. And it's all about the computation of the non-triviality of the wheel W7, which is computed out by finding sort of an explicit linear combination of graphs that witnesses that non-triviality. And it's quite remarkable that they were able to do this, but on a philosophical level, that is now subsumed just by the G equals 7 piece of that theorem, the sort of transcendentalness of zeta of 7. So this was sort of a reckoning for me as a combinatorialist, that the data in question appears entirely combinatorial, but it seems that key advances remain transcendental in nature. Okay, that's it. Thanks for your time.